and welcome to our new classroom. Um, don't get too comfortable. Next week, I'll move us to someplace different. No, just kidding. So, yeah, it'll be musical classrooms at 8 a.m. All right, so last time we were talking sort of the final bit of integer storage, and uh, we were discussing that the um, the arithmetic structure of a computer is different than the arithmetic structure of a human. Namely, since we are forcing ourselves to stay in with a fixed number of bits, then things work more like clock arithmetic than they do sort of grade school arithmetic. Okay. So the next thing we're going to talk about is we've been talking about integer storage. So how do you store whole numbers, possibly positive or negative, possibly just positive, depending on what situation you care about. Um, so today, what we're going to look at is how do you store or start to, how do you talk about non-integers? So 3.7 or 5.2 or whatever. Okay. So such numbers we'll call floating point numbers. And I have to say in advance that doing 8-bit floating point is a little bit ridiculous because of just how imprecise it is. But it'll sort of force us to recognize the imprecision that's inherent here. Okay, so before we kind of get into the binary aspect of this, so like we did with integers and the two's complement stuff, we first looked at stuff in base 10, the sort of usual human system, okay, and then analogized from that to what things would have to look like in binary, okay? All right, so the point of floating point, if you'll pardon the pun, is really two things. We need to be able to express big numbers and small numbers, but when I say small numbers, I don't mean like negative a billion. I mean something like 0.001, right? So really, really small in that sense, but also still be able to do really big numbers like a billion, okay? Now, in 8 bits, we won't have that as much flexibility. Our range of numbers that we can express will be very limited. If we did this with 64 bits, then you can do really, really, really precise arithmetic. Um, but let's think for a moment. Like Henry, what's your favorite big number? Really big. Hmm? 4 million. Can anybody top that? Okay. Well, now we're playing the Price is Right, right? Okay. Now, like, really top that. Yes. Okay. Really, really top it. 8 trillion is. You think outside the box, guys. Infinity's not a number, so you can't do that, huh? A Google. Yeah, okay, that'll work. All right, well, let me take mine. It's not necessarily my favorite. Okay. Uh, now, normally this would be the good setup for a good Yo Mama joke, right? What's your favorite really, really big number? Well, the mass of your mama in kilograms, right? But anyway, right? So let's just take a big number like 6.022 times 10 to the 23rd, right? I mean, 4 million's big. 6.022 times 10 to the 23rd is really big. But could I have taken Henry's 4 million and written it kind of like I wrote Avogadro's number? Yeah, I could. And what would it be? It'd be 4.0 times 10 to the what? Sixth, okay? All right, great, right? So scientific notation, right? Something that you guys all hopefully saw in high school, and you maybe haven't used it in a little while, okay? But we've all seen it before. This isn't like foreign rocket science voodoo math stuff. No? Okay. All right. So what are the rules of scientific notation? Yes. Keep talking. Ah, okay. I see what you mean. Okay, good point. So let's actually talk about 4,000,023. Okay. How would I write this in scientific notation? Yeah. Right. I'd have to either write it like this. Oh, sorry, 10 to the 6th, not 10 to the 23rd. Um, bonjour, vous êtes tard. Pourquoi vous êtes tard? Ah. So, okay, I could write that, and that, you could argue that in this instance, that's kind of a silly way to write that number because it takes way more work to write 4.00023 times 10 to the sixth, right, than it does to just write down 4,000,023. Okay, so yeah, that actually is a good point that if you mix really big with really small, okay, and in a sense, 23 compared to 4 million is small, right? But it could also be something like if I had, Avogadro's number with a one at the very end of it, right? Like that's so far down the line. Do you really want to write down 6.022 20 zeros and then a one or something, right? Like you wouldn't write that. Okay, so subject to rounding, yes. Okay. What other either issues, restrictions, good things, bad things about scientific notation? You can. Okay. So what would that look like? Yeah. Okay. So if I had something like this, just say, then I would write that as 2.0 times 10 to the -4 exactly. And then you're just counting the spots, right? So anytime that you move your decimal point to the right, um, in your okay, and right versus left, we have to talk about which number we're using. If you start with the non-scientific notation number, then moving to the right indicates a positive exponent and to the left a negative. If you're doing it from starting with the scientific notation number, it's of course the other way. Okay, so you got to be a little careful which direction you're going. But we can have negative powers just like we can have positive powers. Okay, and this is what allows us to precisely or compactly write down really really tiny numbers. So if we find some really tiny number, um, let me see. So here's a really tiny number. Okay, this is the universal gravitational constant. Um, it happens to have units that, okay, whatever, but we don't really care about the units for now. I just take that as an example of a really, really tiny number, okay? But the scientific notation system allows us to represent that just as easily as Avogadro's number. Okay. All right. So if we take, let's actually take our 6.674 times 10 to the minus 11, or our 6.022 times 10 to the 23rd. Okay. What things do we have there? Okay. So what like discrete pieces of information would you have? Well, I have these guys. Oops, that's not what I wanted. I wanted the highlighter. I've got these guys, right, which we call our exponents. Oop, damn it. Right, so the green highlighting, those are the exponents. Okay, what else do we have? Oh, come on, guys, wake up. It's right in front of you. The what now? Okay, so this thing here, okay, which this you wouldn't know necessarily off the top of your head before, we're going to call the mantissa. Okay, we've also got the fact that um, we're doing this in base 10, so we need to specify the base, right? Now that said, like in normal everyday scientific notation, do you really have to specify that it's 10 to the whatever? I mean, we do, we write it that way, but would you really have to? Right? So if somebody told you mantissa 6.674 exponent minus 11, you'd be like, oh, it's probably this is what they mean. Okay. Just for sake of completeness, I guess. Right? I mean, does it really break my neck to write it down? No. Now on the computer, I want to reduce how much I write, and so we won't encode what the base is on the computer. Okay, so but we'll get there. Okay, and then the last thing, and it's missing in both of these examples, is because both of these examples happen to be positive numbers, I could also do this with negatives, right? So there could be a sign, okay, plus or minus. Just both of these examples happen to be plus. Okay, so the things that we have to do to express scientific notation is we need to know what the mantissa, so the part before the times 10 to the whatever is, the base, the exponent, and what the sign is. And if I told you all four of those things, you could reconstruct the number. If we agreed in advance that the base would always be 10, then I would only have to tell you three things: the mantissa, the exponent, and the sign. Okay, is that okay? Yeah. But that would be assuming that we'd agreed that the base shall always be blah. Okay, and in the science world, right, the base is always 10, right? So we don't really need to specify it. We just do for sake of completeness, I think. On the computer, what's the base always going to be? 2, right? Ones and zeros. Okay. So because that will be a universal thing, it will always be 2, then I don't have to specify that in advance. We just know that the base is always 2. Okay. So so those are the 3 or 4 parts, if you count the sign, of scientific notation. Okay. Now the other thing is, let me take the 6.022, just for sake of example. Okay. Are those the same number? So 6.022 times 10 to the 23rd versus 60.22 times 10 to the 22nd. They represent the exact same number, okay? However, which one of those would you expect to see if you popped open your chemistry book or whatever? You would expect to see the top one, okay? Why is the bottom one sort of bad, in a sense? It's more than 10, or maybe another way to put it, more than one digit before the decimal point, okay? And the only reason that you would write something as 60.22 is if you were like, let's say that I was adding two scientific notation numbers together and they had different exponents. In order to add them, I have to get their exponents the same, and then I can do it, right? So what we'll do is we will call this form the form that looks normal, okay, the way that we're expecting to see it, we'll call that a normalized number, okay, meaning everything is sort of obeys the usual rules. And anything that doesn't, we'll call denormalized. On the computer, there will be some sort of weird examples of denormalized, but we'll get to that later. Okay, so when I say denormalized, I don't want to make it seem like they're verboten, like that thou shalt never, under any circumstances, use a denormalized number. That's not true. As we'll see, there are instances where we need to denormalize a number deliberately in order to do like arithmetic or something. Okay, so yeah, so denormalized numbers are on the table, but we'll deal with the details of them later. Okay, so in particular, what makes this form normalized? Okay, so what's the sort of magic, or, well, what's the condition that makes it normalized? Yeah. Okay, 1 and, well, 9, but yeah, because if you had 10 point something, you would really write it as 1 point whatever and then up the exponent, right? Okay, so the digit that appears before the decimal point is any digit from 1 up through 9. You would never put a 0 there, because if you did, then there's a digit somewhere else that you could have put in front and played with the exponent. Nor would it ever be 10 or bigger, for exactly the same reason as here with Avogadro's number, right? 60.22, well, I could just shift the decimal point one more spot over and have it 6 point whatever, which is in the form I want, right? So the digit before the decimal point, yeah, okay, so let me write it this way. Okay, it could be any of the digits from 1 up to 9. Cannot be 0, okay? And it cannot be 10, that's not a single digit, right? So it's something between 1 and 9. What follows after the decimal point can be whatever it needs to be, right? 0.022, 0.22, 0.00002, whatever, right? Okay, so there's no restriction as to what's going on after the decimal point. It's only that right before it, we want a single digit, that's it. Yes. No. Okay, so example, how could we normalize this? That would be its normal form. Same number, right? Okay, good. Yes, the digit in front of the decimal point shall not be a zero. Okay. I I mean, look, in science class, is anybody gonna like would Dr. Porter take off points if you put point oh or point 0.5 times 10 to the something? You think he would? Okay. I don't know, maybe he wouldn't. Um, Actually, I think Dr. Porter would be more likely to tell you, you must construct additional pylons or something like that. No? Do you get it? You don't get it? Okay, how many of you guys know what it means to need to construct additional pylons? How many of you have no clue what it means to need to construct additional pylons? How many of you guys have never played StarCraft? Oh, you guys are killing me. Yeah, you're killing me, Smalls. I wonder if Dr. Dunaway's on class this morning, but no. Yes, it's a game. PC from back in the 90s. Well, okay, and then there was StarCraft 2 that was released like 10 years later or something, right? Kids these days. Um, okay, so great. Normalized number, digit before the decimal point shall be something from 1 to 9. Thou shalt not use 0. Um, and that's just the system that we've all agreed on, and great. Okay, now what we want to do is start to talk about how do we make this computer version, okay? There's two things that are going to change. Well, many things that are going to change. On the computer, how many digits do I have to work with? Precisely two, either 0 or 1, okay? And what this means is if I have a normal number and I said that the thing that's before the decimal cannot be a 0, in base 10, what could it be? 1, 2, 3, 4, 5, 6, right, all the way up to 9. I have no idea which digit it's supposed to be, right? It depends. However, if I'm restricting myself to only using the digits 0 and 1, and I said you can't put a 0 there, then what do you get to assume is there? A 1 automatically. Okay. So, um, yeah, so let's go over to a clean sheet here. Okay, so binary. Like with everything in binary, there's only two digits, 0 and 1. Okay, so the first thing is I'm not going to talk about the decimal point anymore because the word decimal is sort of biased, right? It's base tenist. That's a joke, right? Okay. Well, to call it base tennis is a joke. All right. So what do I mean that I'm not going to call it the decimal point anymore? Yeah. Exactly. Right. It's not the right word because it carries with it the essence of base 10, and we're not working in base 10 anymore. So what are we going to call that dot instead? We still need it. We'll call it the radix. Of course, right? Yeah. And this actually is from a Latin word, not shockingly, that means root. Okay, so kind of makes sense, right? It's the root of the floating point number, right? Everything sort of is based around where that thing is. Okay, um, um, and I think it's actually also related to the word radish, as in the vegetable. Um, yeah. Yes. Well, okay. Here's your liberal arts education moment for the day. What is Dr. McKinney's favorite word in ancient Greek? Okay, this means radish. Okay, this word uh, is a verb to radish. Now I'll leave it up to what your imaginations for what this happens to this radish. So it means to thrust a radish up, you know, up your tuchus. Uh, it was a punishment for infidelity, and it appears in one of Aristophanes' plays called The Clouds. Huh? In a sense, right? Like literally, it means to shove the, but it's literally to radish somebody, right? Yeah. So yes. So yeah, the question is how often were they doing this? Well, okay. So with that, I have to wonder if actually what's happening here is that Aristophanes just made up the word, right? In the same way that like we do this in English, right? Where you might say, um, of course, I can't think of an example at the moment, but well, like earlier we were talking about schlepping, right? And so I said schleppage, as in like the concept of having to schlep something for somebody, right? I just basically made up a word, right? And one of the things that's so lovely about the English language is that we can do that sort of thing freely, and nobody yells at us for it. Unlike French, say, where the Académie Française is going to be like, "Oh, that is not French," right? And they, "C'est pas français, c'est mal." Um, yeah. So anyway, okay. So there's your fun lesson for the day. All right. So let's erase the evidence, um, even though it's out on YouTube. Okay. Yeah. Well, I haven't affiliated, right? So yeah, I'm going to get like a takedown strike. Use of ancient Greek profanity, violation of terms of service, section 2.3 point, subsection 4 or whatever, right? Um, okay, so we'll call the decimal point the radix, not the decimal point, when we're working in any base other than base 10. Okay, so there's a minor change. And then also, um, in a normalized number, we get to assume that the digit that's immediately before the radix is a 1, okay? Because we said whatever happens before the decimal point cannot be a 0, and that in binary leaves only one choice. It's got to be a 1, okay? That in binary is very convenient because what it means is that we get a bit for free. We don't have to encode that 1 because we assume that it's there, right? So if I'm going to do an 8-bit floating point number, in a sense, I'm really doing a 9-bit floating point number. I just don't encode one of those bits. I don't need to because it's assumed to be there. Okay, that's kind of handy because yeah, like I said, we get a little bit for free here. Okay. The other thing that's different, of course, is that the base is 2, not 10, right? Because we're doing things in binary, not base 10. All right, so if I were to write, for example, 1.1 times 2 to the first, well, okay, maybe that's a bad example. Let me do say 2 to the second. Then what is this number? This would be 110, which means, oh yeah, 6, thank you. It's 6 in base 10, right? Because I got a 1 in the 4's place, a 1 in the 2's place, and nothing in the 1's place, right? Okay. Now, how many of you thought that this would be the number 110? Okay, good. Right? It's not 110 because we're working in binary, not base 10, right? Okay, so why is it though? This is a good question. How is it that I knew to shift the radix to positions? Yeah? Yeah, because the exponent is a 2. Okay, but here's the thing. Moving the radix in base 2 is tantamount to doubling the number. Does that make sense why that's the case? All right, what does it mean to move the decimal point one's position in base 10? If you move it one way, you're multiplying by 10. If you move it the other way, you're dividing by 10. Okay, and what makes base 10 arithmetic so nice is that just simply moving that dot is enough to do multiples or of 10 or divisions by 10. Okay, so I'll tell you guys a good story about that and how, some people are idiots. So back when I was in college, I had a job. Actually, I had several jobs, but does anybody happen to know one of the jobs I had in college? Have I told you guys? No? Okay. I worked at Kohl's. Okay. How many of you guys have shopped at Kohl's or your mom shop at Kohl's, right? We're here in the Midwest, of course, right? I was employee number 1245936. Nice to meet you. Will this be on your Kohl's charge today, sir? Oh, you don't have a Kohl's charge. Well, we can sign you up for one and I can save you 15% off your purchase today. Yeah. Okay, so what? Yeah, I said plus you get Kohl's cash, right? Or whatever. Um, all right. So anyway, I worked at Kohl's, and um, what invariably happens, the busiest time of the season at a store like that is at Christmas. So right before Christmas, it's the mad dash, and then the day after Christmas, what begins? Two things. Re- huh? Sales and Return-a-Palooza. Okay, when everybody's returning stuff. Okay, so in particular, the sales, right? We've got leftover whatever Christmas and other holiday decoration stuff, and we want it the heck out of the store because the Valentine's stuff will be on the truck like tomorrow, kind of thing. Because you know how stores are, right? I mean, Walmart probably already has their Christmas stuff up, which is ridiculous, but whatever. Um, okay, so it's a couple days after Christmas, and I am uh, uh, doing something on the sales floor rather than where I normally was stationed. And a lady comes up to me and she says, "Can you tell me how much an item is?" Sure, right? She's like, "Well, it's all part of the Christmas stuff, and all the Christmas stuff is 90% off." Okay, now to be fair, uh, retail establishments don't really make it easy when they say 90% off. 90% off of what? What do they mean? Okay, so what do they mean usually when they say that? Off the sticker price. Okay, so if you look at the thing with the barcode, it says the MSRP or the original price. That's the magic number that determines everything else. Okay, um, so if the original price on this statue or whatever was $30 and all the Christmas merchandise is 90% off, then how much is that item? $3. Now, how did you do that so quickly? Exactly, right? 90% off is the same as 10% of, right? And then computing 10% of something is easy because you just divide the number by 10 and 30.00, which is what the price tag says, just pop that decimal point one spot to the left and bam, $3. Okay. So great, off she goes. So she comes back maybe 15 minutes later with a cart full of stuff. She's like, can you tell me how much each of these items are? And I'm like, yes, ma'am, of course, right? Surface with a smile. Um, so, I'm grabbing things. I'm like, $3, $2, $2.50, right? And she's like, how are you doing that so quickly? You must be really good at math. I'm like, well, I do happen to be a math major. Wow. But that's not why it's so fast. And so then I explained that to her. And she's like, her mind was like blown. This was, a middle-aged, she was probably in her 50s or something at the time. Like she was just floored. Okay. So, point being though, moving the decimal point is just in base 10, multiplying or dividing by 10, depending on which direction you go. So accordingly, if we do this in binary, moving the radix is tantamount to multiplying or dividing by 2, because that's the base. Okay, same logic. Okay, it's just that you're not used to working in binary. And oh, could you imagine if we priced everything in binary at Kohl's? Right, that would be a train wreck. Yeah. Okay. So that part of it will work exactly the same way. Okay. It's just that it's base 2 instead of base 10. Great. All right. Now the other thing that I've sort of done here, and so let's look at two things that I wrote. Okay, I wrote two twos. The blue 2, the first one, the base, did I need to even write that? Well, yes and no. Okay, yes, in the sense that you guys aren't all psychic, but no, in the sense that, well, if we decree moving forward that we will always write things in base 2, this being a computer science class, then I don't really need to specify the 2 because you guys know that, well, what else would it be? It's not as if I'm going to suddenly do something in base 17 one day just to keep you guys on your toes. Um, okay, so I didn't really need to write the blue 2. What about the red 2? Did I need to specify the red 2? Definitely, okay, because that tells you how many spots, if any. Um, the exponent could be a 0, right, which means don't move the radix at all. But I needed to specify that to tell you how many positions to move the radix. Okay, great. So I needed to specify it. How did I specify it? How did I specify the exponent here? I used a base 10 number to represent a piece of information that's supposed to be a base 2 thing. Okay, so when we encode our exponents, how should we be encoding them? And with zeros and ones, okay? And because we're trying to do everything in binary, okay? So what I'm going to say here is, oops, um, the mantissa is going to be everything that comes after the radix, okay? Now, in base 10, when I wrote 6.022, did I include the 6 in the mantissa? Yes, because I couldn't assume that the 6 was going to be a 6. Maybe it was a 7, maybe it was a 3, I don't know. Right? But in base 2, what do I get to assume? The thing that's before the radix is always a 1. And so I don't need to include it in my mantissa. Okay? All right. Now, the other thing then would be my exponent, which how did I write it? I wrote it as this, but what really do I mean there? Okay? Okay, and if I put one way that we try to deconfuse this in writing is if I mean that it's a base 2 number, I'll write a subscript of a 2, like the word 2, um, or do like what we've been doing, and we'll get back into using this notation where I write 0b something, okay, to indicate that it's in binary. Okay, then the last thing that I would need to specify, I don't need to specify the base, right, because we're assuming that's a 2. What's the one other thing that I need to specify here? The sign, okay, that this number is positive. And the standard that we're going to use is if the number you're dealing with is not negative, then you put a 0 as its sign bit. And if it's a positive, okay, so if it's the number 0 literally or positive, then the sign bit is 0. And if the sign bit's a 1, what does that mean? That it's negative, okay? Now that's nice because when we were doing things with integers, what bit told you whether or not the number was positive or negative? The one on the far left, okay? Whether or not you call that the first or the last depends on your point of view. And that we call Indianness, like ENDI, not INDI, yes. If you had it on a computer, if you had the number like 6.3, how would the computer? You wouldn't. You would have to encode it in binary. So how would you know? What do you mean? So like in binary, it's easy to represent integers because you have a sign bit that's negative. Mm-hmm. So if you wanted to represent 6.3, the first thing you would have to do is write it as a binary fraction. Now the 6 part's easy, right? But what's 0.3? 3/10. Okay, now you have to come up with a way to write that as how many halves, how many quarters, how many eighths, how many sixteenths, and so on. And that may be tough. Well, I mean, but there's like on that bit left to right, there's nothing that represents a fraction. There's nothing that represents it like smaller than 1. So like that's why I'm confused like how it represents it. Okay. So Cole's question is, how do you represent information smaller than 1? Well, so somewhat the answer to that is, how did you know if you wrote 6.022, no times 10 to the whatever, just the number 6.022? How do you know, like, or better yet, let's just take your original example of 6.3. Okay, close enough. 0.3, the 3, how much does that count for? How did you know that? Because you're not an idiot, right? You've done base 10 math. Okay, but how really do you know that? You know it's in the 10th position, right? Because it's one spot to the right of the radix, okay? And then spots to the left of the radix, they all go up by powers of 10, right? So you have your ones place, your tens place, your hundreds place, and so on. And if you go the other way, it's your tenths place, hundredths place, thousandths place, and so on, right? Okay, well, that same thing is true in binary. It's just that instead of tens, it's twos, right? So counting up from 1, what are the bit positions? Ones place, twos place, fours place, eights place, sixteens place, and so on, right? What's it to the right or to the other direction? Halves place, quarters place, sixth or eighths place. Yeah, it works exactly the same way. It just doesn't feel as intuitive to you, right? Okay. Now, obviously, we've got a lot more to talk about with this stuff, but yeah. Okay. So we've got a couple of decisions to make. Well, I say we have a couple decisions to make. I'm going to make them, but I have to encode 3 things to specify a floating point number. Okay. I need to encode the sign bit. Well, that's easy. How many bits does it take to encode 1 bit? I don't know. How about one, Dr. McKinney? Right? 1 bit for the sign. Okay, great. Well, then I have to decide how many bits am I going to spend on the exponent and how many bits am I going to spend on my mantissa. Okay, and I also need to decide how many total bits I'm going to use. Okay, and the convention that we use for 8 bits. Well, actually, you know what? Let me show you something first. Okay. So no, I'm not looking up like things to like, you know, get in the pool with. Okay, so this is a little trinket website called Float Toy, and I'll put a link to this up on Canvas, um, and for floating point toy. So here, what this has done is show you, and it loads, for example, how to encode pi, the 3.14 number, in the floating point standards um, for using 16, 32, and 64 bits. Okay. What are we going to do? We're going to do this in 8 bits, which sounds crazy and it's horribly imprecise, but that it's easy to write down. Okay. So look at all 3 of these things, right? How many bits are used for the sign? He's even color coded them to make it really helpful. Right, the sign bit in all 3 examples, it's a single bit and it's the far left bit. Okay, so that's nice. That's the same as it was with integers. Okay, convenient. Okay, the green stuff is the exponent. Okay, and the red stuff is the mantissa. Okay, but what I want to sort of look at is what sort of roughly, and we don't have to be precise on the count here, just for right this instant. What's the rough ratio between the number of bits for the exponent versus the number of bits for the mantissa? So in the 16-bit case, how many bits do we have for the exponent? There's just 5, okay? And we spent 1 on the sign bit, so that leaves 10 left over for the mantissa, right? So that's a ratio of 2 to 1, basically, right? We're going to spend more bits on the mantissa than we do on the exponent. And then we don't have to count the other 2, but we can see that that same thing is true. And in fact, it's even perhaps more exaggerated. With the 64-bit, there are way more mantissa bits than there are exponent bits. Okay, so if we're going to do this in 8 bits, we need to decide how many bits are we going to use for our exponent and how many for our mantissa. Okay, and the convention that we're going to use is 3 bits for the exponent, 4 for the mantissa. Okay, for 8-bit. Now, I should say, and we'll kind of use this to finish today, it's not as if he just made up, I'm going to use 5 bits for my exponent and 16 bits and the other 10 for my mantissa, right? He didn't make that up. Okay, there's a standard for this, and it's called IEEE 754. Okay, so in the 80s, 1984 is when the first version of this came out. Bunch of computer people got together and said, all right, we need to come up with a standardized way to represent floating point numbers on our machines that everybody will use, and then nobody will be confused. Okay, seems like a logical thing to do. And then the standards that they came up with were for 32 and 64 bits floating point numbers. Then later, it turned out to be useful to have 16-bit, which is more imprecise but useful in a few other contexts. And so what I'm going to do is we're going to look at basically take the standard, which doesn't define an 8-bit system, and follow all the other rules of the system, except do it only in 8 bits. Okay, Gucci? All right, so we'll quit the stream, quit class, and we'll talk about more of this on Friday. See you guys later.